at a part in 10 to the 5 in those maps. Then these sound waves have frozen out, and to first order, they've just persisted ever since to the clustering of matter, dark matter, formation of galaxies occur at these same locations. And so here's a CMB map from Planck, the acoustic scale. Here was one of the early measurements of the acoustic scale in galaxy maps. So this feature that's a part in 10 to the 5 becomes a feature of the part in 1 to the 10 here in the galaxy maps. So it's actually almost an easy measurement to make once you have a large enough map. Okay, and then today, most of the energy density in the universe appears to be in dark energy. And I'm just showing this because the simplest parameterization of this is you have a cosmological constant. But then the next order thing to look at is if dark energy is dynamic, meaning it can change with time, is basically just a Taylor expansion of like, okay, if you have a field that's changing, how do you write that down? Lots of different models on how to do this. People in the room here who you should talk to instead of me about what that means. But this is observationally just how we parameterize this to make a measurement. Okay, so today there are actually quite a few projects aimed at doing this. So making large-scale maps of the universe to measure dark energy, but other things as well. So these are the 6 biggest ones. And I should say the only one that's really in an operations phase right now is DESI. And it's so it's the one that started first, and it's actually going to be the largest of these 6. So we kind of have a head start. And then, well, I guess Euclid is the other one where they're actually collecting data. So they've actually started. Before making that 3-dimensional map, you have to make a 2-dimensional map. So this we actually started a long time ago. We actually started this in 2013 to make a map of about half of the visible sky in 3 filters, such that we could then select galaxies that we'd be targeting across cosmic time. So this map, it's actually all public data. It was done as a set of 3 coordinated public surveys. It's actually still ongoing today. We can't seem to end this project. But to date, we have catalogs now of, it's about 1 billion galaxies on the sky, of which a few % are the ones that then we're following up on to make our 3-dimensional maps. And these are public, and there's actually a fun web portal where you can just drive around the sky and look at things. And this is that same part of sky. This is what our view of this looks like now if you measure redshift. So this is kind of the density of objects that we're measuring. And there are some stars in here too, but you have to invite someone else to talk about the stars. Okay, so here's a real picture of the telescope without a transparent dome. So this is at Kitt Peak in Arizona. And the primary mission of this project is to measure the acoustic scale to a % level precision at 20 different redshifts. Oh yeah, and I should mention something I love about this is actually the same telescope that Vera Rubin used to discover the effects of dark matter back in the 1970s. So it's a nice historic site. Okay, so I'm going to tell you a little bit about what the instrument looks like. So for the construction project, we kept the telescope. So this part here is the same. We kept the dome. We kept all the asbestos, unfortunately. But what we replaced, this whole top end of the telescope actually came off. So that was just like sawed off or whatever you do to take off the steelwork. And what we have in its place is it's a set of 6 large lenses that correct a large field of view that's about 3 degrees across. And then on the top of the telescope, there are a set of 5,000 optical fibers that then lead down to the instrument room. So the instrument room is it's a clean room down here that has all the instrumentation. And that includes, it's 10 spectrographs, each with 3 cryostats. So it's actually quite a big instrument. The point of all this is so that we can look at more than one galaxy at a time. So if you go back to when I was a student, people did these redshift surveys looking at one galaxy at a time. You can do that, it just takes a long time. So the name of the game here is really to multiplex these observations so we can observe as many galaxies at a time. And so currently this is the largest multiplexing by observing 5,000 galaxies, and we do this every 15 minutes. Okay, so this is what one of these optical lenses looks like. This is to correct that field. So this lens, it's 1.2 meters in diameter. And I can still say this is the largest lens on any telescope today. Rubin will have a larger one, but they have not put it on their telescope yet. So the statement is still true. This is the focus of the telescope. So actually at the top end of the telescope, we have this fiber robot army. So it's 5,000 miniature robots. So it's about the size of, these are about the size of your finger, that can move a fiber optic around to the location of galaxies. And here's just a little zoom in on some of these. So these were actually these were all constructed by hand by mostly students at University of Michigan. And there are about 600,000 parts in this. Anyway, we can talk about this at dinner if you want, but it all works, okay? And we can reconfigure the locations of all these in about a minute. And for those of you who build things, the precision at which these point on the focal plane, the mechanical precision, it's about 2 or 3 microns. Okay. Then the instrumentation, the spectrographs. So we have 10 of these. It covers what we call the full optical range. And what that means is all the wavelengths that silicon detectors work efficiently at. And so this is uncrating them in this clean room, the second to last one being installed. International collaboration, it meant we did lots of shipping. This was us, those large lenses actually traveled around the world before they made it to Arizona. Their final location was actually in a basement in London across from the British Museum. And we had to then ship them from there to Arizona. And this was done prior to the Ukrainian war when we were able to charter a Ukrainian troop transport plane. So this is how we shipped that business off to the telescope. Yes, some assembly required. There's actually a disassembly of what used to be on the telescope. And the only way to do that was through the opening of the dome. So that was exciting. This whole installation, after we built everything, took about 1.5 years just to do the de-installation and the installation. For any homeowners here, that sounds fast. Everyone else, I know it sounds slow. And this is this actually has all those lenses. So this is a 6-ton beast with all those meter scale lenses being put up on the top of the telescope. Okay, and here's our first light. So it was, well, a few years ago now, where we just pointed at the Triangulum galaxy. And the reason we did that, this was our first exposure on the sky. We didn't necessarily know where everything was pointing, but this is a big galaxy. We're like, we can't miss. And indeed, we got a nice spectrum of the Triangulum galaxy. So that was our first light where we just had part of the instrumentation. But this gives you a sense of also how much of the sky we could see, relative to the full moon. So it really is by any standard large field of view. Okay, then we started the next phase of the project after we got everything installed and operating. Then we had this survey validation to just tune up what the survey would look like. We started this March 14th, 2020. Does anyone know what was happening in March 2020? Yeah. So fortunately, we got 2 nights of data, which was like, it's actually infinitely better than 0. So we wound up being shut down for about 6 months, but this didn't actually really cost us 6 months of time, because just with a little bit of data, you can really learn a lot. So we were able to get back in the sky that November in a very different operating mode, as you can imagine, since no one could actually be in the same room as anyone else. But again, this didn't actually cost us very much. So then we started the survey proper. It was the following May. And this is actually, it's a dedicated instrument, meaning we're not sharing this telescope with other instruments or projects or anything like that. This just runs 365 nights a year. We have had some other issues. So the year after that, there was a forest fire. It actually overburned the site. So this fire line went right across the mountaintop with the telescope. Our telescope was actually the safe building for the firefighters to retreat to so they wouldn't die. So it burned the roads, the power, the internet, everything, but the telescope was fine, and actually we were up and running, just a number of weeks later, even though we didn't have internet or power or anything, we were back on the sky. Then the year after that, pirates, just giving you the sense these projects, you have issues. So we actually lost access to the observatory for several months. But we've been through episodes like this before. We had the Contreras fire where we didn't have connection. So this was another period of time where people are running up and down the mountain with disk drives and whatever, but we kept operating. So we lost no time because of pirates. And in fact, as a whole, we're ahead of schedule. So this is how many galaxies we're measuring redshifts of. And like this here, this was the Contreras fire. These episodes are reflected in this curve of how quickly we're running. But we're running. And so at the moment, this is as of last night, 33.6 million galaxies. The design of this project was initially to do 40 million galaxies total. We're going to overrun that, clearly. And just as a comparison, this is adding up every prior redshift survey done by anyone on planet Earth before this, and I get 5.0 million. So it actually supersedes everything prior, including SDSS, however much I love SDSS. Okay. Okay. What does the data actually look like? So let's go to the data now. This is our typical spectrum of a galaxy. So these are the data we're using to make these three-dimensional maps. So that's a spectrum of this little galaxy right here. Really doesn't look much. What you see here, it kind of looks like noise. Why does it look like noise? Because it is noise. It's mostly noise. We're mostly collecting noise. We're mostly getting spectra of the night sky. But we have a lot of wavelength channels here. And if you zoom in, you can see this is it's called the O2 doublet. So it's singly ionized oxygen. This this is exactly the same data. Sorry. My guess is this just happens to be a noisier detector channel. We have a lot of detectors, and some of them are a little noisier than others. I don't actually know offhand. Yeah, I mean, this was from early data, so this might be some issue we solved. I mean, a good eye. I don't actually remember though. Okay, but even though most of our data is noise, we can see these features. This is actually a very distinctive feature. This is kind of an interesting one because you can't actually even measure this transition feature in the lab. The Einstein A is just like too small. You never actually get this transition in the lab because ionized oxygen thermally de-excites before it can actually emit this photon. It needs to sit in a vacuum for millions of years before you actually get this transition. So you do get that in X-ray galactic space. So even though you can't actually measure this wavelength in the lab, this is the primary feature we're using to make these three-dimensional maps.
Explanation about 1928.
Okay. Okay. All right. Okay.
It's just the number of the permitted lines, resonant lines are just stronger. So you'll see it. You just have the sensitivity. You just need a long pathway.
Okay. Okay.
You don't get on top.
Okay. All right. I stand corrected. Thank you. All right. All right.
Terrestrial conditions, the lines just go to Boltzmann distribution, and you just see that. But that coefficient is proportional to A. A is small.
Mm-hmm. Good. Good. Okay, we do have some data that look better than this. So this is an object. This is actually still a pretty faint object. So this is a quasar most of the way across the universe. But we still get very good data on this. This isn't actually noise that you're seeing here. This is actually hydrogen absorption between us and this distant object. No, okay. So from all those galaxies, we measure these spectroscopic features. We measure a redshift. We turn it into a three-dimensional map where the map is actually, it's the angular position on the sky and the redshift. So it's not a true distance. It's the redshift distance. But then this is then this movie of these are the 5.7 million galaxies used in the first year of data for our first cosmology results. Okay, then what does this look like? So we were talking about the acoustic scale previously. So this acoustic scale, we can look at either in configuration space or Fourier space. We do both you're looking at the same thing, it's the same data, it's just a different analysis. So, in configuration space and real space, this is a sound wave. There is just a distinctive scale for it. If you take a Fourier transform of that, it looks like wiggles. So people often talk about this feature as the BAO wiggles because they're thinking in Fourier space. Okay, so this is fundamentally the data that then goes into our first year analysis. So we have different kinds of galaxies that we're measuring at different distances. These are the measures of the acoustic scale at each of these different distances for these different kinds of objects. The two most distant ones are from quasars. These data, something I didn't mention was these data were actually blinded for this whole analysis. So this was the first time we really did this in this kind of experiment where we took that three-dimensional map, we actually modulated the distances to all the galaxies in an approximately self-consistent way, just so that we didn't know the answer until we were unblinding. But what you can see is this is a very high signal-to-noise detection of the acoustic scale at all these different redshifts. Prior to our results, this is all plotted, the acoustic scale distance as a function of what the best fit cosmology was prior to DESI. And you can see some deviations of these data relative to that best fit cosmology. And so the dotted line is where we want to push cosmology to actually fit these data. Okay. Then we can ask the question of, this is a projection of the constraints from each of these different samples of galaxies. They're all consistent, which you can already see in that you can draw a line through all of these observations at different distances, refit a cosmology that's consistent. And then you can start looking at what is that cosmology that we're fitting to. So one of the things that comes out from this is the universe is spatially flat. There's not a curvature component to very high precision in these data. There wasn't prior to DESI, but this actually pushes that down even further. Neutrino masses, or the sum of the neutrino masses, affects this as well. This has kind of been an interesting part of the results from DESI. So this actually affects the late time evolution. There is a degeneracy here between what the Hubble constant is, the current expansion rate of the universe, versus what the neutrino masses are. We're actually pushing up against what the minimum neutrino masses must be just from neutrino oscillations. So actually, if you just interpret these data right here, this is arguing against inverted neutrino hierarchies. We're really pushing the data actually prefer a zero or negative neutrino mass, which is unphysical. But what this is telling you is the data really is pushing you to a low neutrino mass. Okay. Then there are certain controversies or tensions in cosmology today. One of them is the Hubble tension controversy. So what is the current expansion history or expansion rate of the universe? There's all of these measurements more from the distant universe that's preferring a low value of this. But then there are late time measurements. So these are direct measures of the local universe, where there are some groups that have been arguing for a higher expansion rate. The DESI data actually falls right in line with these other more distant measures of the Hubble constant. So this, this doesn't resolve this tension. This just says, if you're taking these other results seriously, you still have this tension.
CMP and DESI, just forget the green points. Are you happy with the single value for the open?
Yeah, I mean, I would say these are all consistent within the error bars. I mean, let me just say yes, yes. Okay, getting back to dark energy, you can ask the question of what models for dark energy fit. So the DESI data itself, actually combined with CMB measurements, this really does zero in on values for W and the omega mass, the amount of mass in the universe. So it's all very consistent and actually consistent with the lambda CDM model. So really consistent with the simplest picture that you could have. But that headline that I started with of like, did we get dark energy all wrong? That comes from taking these results and then looking at them in combination with lower redshift data from supernova measurements. So this is when we take those DESI measures of it's just the BAO scale at these different redshifts, combine it with supernova data sets that are primarily at lower redshift than what we're measuring. This is where everything is suddenly in tension. So in fact, so this is an analysis with each one of 3 different compilations of supernova data sets. These have all been published in the last year. And what this tells you is if you try to get consistency with these data sets, this actually pushes you away from, this would be the lambda CDM model. And at different levels of, well, the deviations here are somewhere between, say, 1.5 and 2.5 sigma. So that's the kind of deviation that we're looking at. So it's not, it's not a 5 sigma detection of anything, and it relies on this joint analysis. Okay. I also want to point out those supernova data. There are folks pointing out possible issues in the supernova data sets. So in fact, this was something published more recently, just saying that these 3 supernova data sets, a lot of them actually include, there are overlaps in the data between these data sets. So they're not 3 independent data sets. So this was looking at a comparison of these data sets. Are they even self-consistent? So this is just one paper claiming that there are issues in here. So this is, I think the jury is still out on this, but this is just telling you there is some level of suspicion in this. And again, if you remove this, then DESI is completely consistent with the lambda CDM model so far. Okay. So what's next from DESI? This is the sky coverage of what I was showing you. So this was based on just the first year of data, so from 2021 to 2022. This is actually our sky coverage as of, well, actually, this is a few months ago now. This is our year 3 data set. So actually, 3 times larger, essentially. And we were actually looking to extend this map to even cover more sky. So what we're looking at now is extending this to something pretty close to half of the observable sky, which is it's essentially all of the interesting sky that we can see from the location of this telescope. So that's currently the plan. And one of the rationales from that is, what if we are seeing a hint of dynamic dark energy? How are we going to confirm that or rule that out? And so one way would be, well, you'd kind of like more supernova data. You'd like a data set that's self-consistent from that. We're still waiting for those next supernova data sets. So the expectation is once Rubin Observatory starts, that'll be providing many supernovae to make an independent measurement of the supernovae. Since Rubin hasn't started yet, that's still some number of years away. But this full DESI program, by observing all of the sky that we can from Kitt Peak, that actually gets us enough sky coverage that we could make measurements of dynamic dark energy to the same precision that I was showing you without any supernova data. So it'd just be internal to what we're measuring from the acoustic scale. So this would be by 2028, we'd have sufficient data to actually do that, and to do that at a 5 sigma detection level. Okay, and just going to take a few more minutes and talk about what's after DESI. So we've been designing what the next experiment could be. So in DOE landscape, this is called Spec S5 for the stage 5 spectroscopic experiment. So this would be an experiment both to measure dark energy, but then also the early universe inflation. And it would make use of, this is the same telescope I've been talking about. So it's the telescope we re-engineered for the DESI project. We'd actually re-engineer this yet again for this next project. And then there's a twin of this telescope in Chile. So this is the Blanco telescope, mechanically identical, although it's a shorter building. But the telescopes are actually identical. So whatever you do on one telescope, you can do on the other telescope. And one of the other advantages of this is then it gives you full sky coverage. So then you can make maps that actually cover the full sky. This is just a rendition by David Kirkby of how big would this next project be relative to, so this SDSS and DESI. So bigger, yes. So inflation, just to talk about inflation a little bit, there are limited tools for trying to measure inflationary physics. And so the two main tools are looking at gravity waves from the early universe. And so there are ways to try to directly see the imprint of gravity waves, or looking at the imprint on CMB polarization maps. The other measurement that we have is looking at non-Gaussianities from the inflationary epoch. And that's what we can do from these galaxy maps. To date, the best measures that we have of these non-Gaussianities, they're actually still from CMB maps, but these CMB maps have actually run out of information for measuring this. So in fact, for these kinds of measurements, you actually want to go to galaxy maps where you get many more modes that you can measure. So this project that we're designing right now, it's designed to measure 10 times more linear modes. And what I mean by linear modes is this is the large scale structure of the universe. On smaller scales, you have clustering of galaxies. You've erased whatever the initial conditions were of the universe. But on the larger scales, that's what we're calling the linear modes, where we're still seeing the imprints from the early universe. And so to measure non-Gaussianity, you really want as many of these linear modes as you can, which means you want volume of the universe, and actually higher redshift helps because you can actually, the universe hasn't collapsed as much. So there are more of these modes per unit volume of space. Okay, so just to quickly show what this is. So this is the telescope we're using right now, the Male telescope. This has a 3.8 meter diameter mirror in here. And then we've put this 5,000 fiber robot on the top of the telescope. Our design for this is we had this miraculous discovery just a year ago that in fact, this telescope is so big and so overbuilt that you can actually fit a much bigger mirror on the same telescope. So this is something that no one even suspected. But in fact, we have the engineering drawings now where you can actually put this much bigger mirror on here. So this telescope, it has a moving weight of 375 tons. So you can kind of put whatever you want there. So this design, it has a segmented 6-meter diameter mirror, 13,000 robots. Actually, sorry, the robots will be down here. And then instrumentation that looks very similar to what DESI has right now. Okay, so I'm going to end with this, which is, this is just the history of redshift surveys from even before my time. So it's going back to the original CFA redshift survey published in 1983. So this was done looking at one object at a time over many years, through to SDSS surveys over many years, DESI, and then we have managed to stay on this curve of increasing the size of these maps by a factor of 10 every 10 years. There's no reason why that should be. It's kind of like the Moore's law for cosmology. We're getting a factor of 10 every 10 years. And yeah, my prediction is we could map, if we stay on this rate, then those linear modes that are most interesting for cosmology, we should measure all of those by 2043, if you're measuring the right galaxies, and then essentially measure every Milky Way type galaxy by 2061. You can ask yourself how old you'll be in 2061. We should be done by then. Okay, I'll stop there. Thank you. The answer is I'll be 94. Okay. Right. So this next project, mostly we're looking at higher redshift because that's where the volume of the universe is. And I should say, this won't be the only project doing this. And in fact, Sphere X will be exploring that starting next year. But this is an optical instrument. And once you're above redshift of 2, then the Lyman alpha, the hydrogen 2-to-1 transition, has redshifted into the optical. So actually from redshift 2 to redshift of 8, it's easy for us to measure a redshift of these objects with an instrument like DESI or SpecS5 or any of these. No, so that's a good question. So so some galaxies are, yeah, these emission line galaxies where you see the Lyman alpha line. Some of them won't actually have that. So we'll actually also detect what are called Lyman break galaxies, which are more massive halos where you don't have that, but you still have a feature there that we can measure a redshift from. Although most of the galaxies you'd be mapping easily are these Lyman alpha emitters. They're in lower mass halos. There are some questions there of, is that a good tracer of the underlying structure? I think that we don't actually know yet.
So if your detection of dark energy radiations, would it make
the Hubble constant discrepancy better or worse? You have inconstant approximation of different lambda.
Right. Yeah, I'm not sure it actually affects that very much. I'm actually going to defer to the answer to that because I'm not sure. What I can say is it helps the neutrino mass limits quite a bit because it actually relaxes that. But what's up? Uh-oh, okay. Right. So it's hard to answer that question right now because it depends on a lot of things. What I expect it to look like just based on initial tests that so we're actually using the DESI instrument to test these things out right now. And what we found is we can do better actually with the same kinds of exposures that we're doing right now, these 15-minute exposures, but we move around a lot more and we observe the same galaxy multiple times. And that happens to just get rid of some, some forms of error that we have in the data. So I expect it'll look more like that, which is different from the way that DESI is operating. We open the shutter, we collect photons for 15 minutes. We never look at that galaxy ever again, like we're done with it. So I think that probably won't be the case for these more distant galaxies. And they are faint. They're really faint. So that's part of the argument for like bigger mirror, more multiplexing, so you can observe longer. It's just I'm saying it's easy to measure redshifts in the distant universe. It's easy if you can collect enough photons. Then it's easy. Okay. Yeah, so good question. Light pollution, Tucson and Elon Musk. So Tucson, historically, the city has done very well at controlling light pollution. We can actually see it if we're pointed lower in the horizon towards Tucson or Phoenix. The sky brightness is a little bit brighter. But what's interesting is we have these two sites where we actually have a lot of data. In Tucson and in the middle of nowhere in Chile. And the sky conditions from these two sites are almost identical. So if we plot up distributions of its sky brightness, its seeing, its whatever, these two sites are largely indistinguishable from an observer's point of view. Okay, then the question about Elon Musk, well, and other satellites. We definitely see them. In the middle of the night, Starlink is not an issue because it's a low enough Earth orbit that in the middle of the night, if they're overhead, they don't see sunlight. Their only problem if you're bouncing sunlight off them back at you. So if they're in the Earth's shadow, they're dark. They're not an issue, but it's closer to sunset and sunrise where you can get reflections off satellites. So we have some observations. It's not a big deal for us yet. So with just the Starlink constellation, we do have some exposures where, rather than seeing galaxy spectra, this was just kind of randomly found by some people in the collaboration, like, on this one observation, there seem to be all of these spectra that look like the sun, and then you plot up where they are, and they're all in a line. It's like, I have a guess as to what that is. So that does happen some, but not terribly often, and only near sunrise, sunset. The issue is there are all these other constellations that will be launched, some of them at higher altitudes, and then there's a longer period where, they can still bounce sunlight and get into your camera. That said, if it becomes a real issue for us, we could just reject those observations because you wind up with the spectrum of the sun. You know what that looks like. So I could foresee a future where we veto some amount of data. I think it's maybe more worrisome for some other projects where it can be more polluting.
Lucky recipient. Big battles fought in the 60s for Mayo, Blanco, and also for the AAT. They're all the same.
Mm-hmm.
Because telescopes after that became Altaz, and you would have been able to see the gift of.
That's right.
And there's a lot of debate that books about this. And tons of steel,
Mm-hmm.
chosen as last conservative gas before.
Mm-hmm. No, that's right. Yeah. So it's completely that these are overbuilt equatorial mount telescopes. If you tried to put this instrument on any telescope built after 1975, it would collapse. Yeah.
Other telescopes which are similar, I think the CFHT also built the same.
That's right.
Same.
Possibly. We've looked at CFHT some. It could be the third telescope here, but it might not actually work for some reasons. I'm not sure.
Other one get freeze AAT, it's the same result.
Right. Yeah. Yeah.
But one question, so in the rest of DESI and the S5, if when that is not changing,
Right.
most of the information precision must come from precision 1.5 to something. So the 2 to 8 is not buying a lot. How many
Yeah. No.
galaxies
So
are there?
No, that's exactly right. So the higher redshifts, we don't expect to see much in terms of dark energy or lambda. That's already quite constraining those points there. So the reason to do those redshifts was for the early universe. That's really that full motivation there. So at lower redshifts, so out to redshift of 0.5, DESI is going to map, half the sky. There's still the other half the sky that we'd like to do. So, another route 2 would be great. And I mean, the same goes up to redshift of 2, because there are these other projects that I was mentioning, but they're not actually going to measure galaxies up to the cosmic variance limit of what you'd like to, by a factor of several at least.
The Spirit totally slightly better than photos.
Yeah, no, so Spherix is designed more as an inflation experiment to look at the non-Gaussianity. And I think, we're very excited to see what it does. So it'll certainly be kind of the best data this decade for those higher redshifts. Once we get spectroscopic information, there's information that's lost in the photoz's because you've smeared out these modes. So if you really want to measure these modes precisely, eventually you want these spectroscopic redshifts. And they're different kind, that's right. Yeah. So it's in detail, it's entirely different. That's right. Sorry, in the which sorry, in Yeah. So these aren't actually independent data points that you're looking at, so you can't actually analyze these by eye. So that's, I mean, the other thing that you'll see, yeah, you see correlated data, and it is correlated data here. So you can't just, you can see the chi-squared looks like it would be too small also. But that's all the correlation matrix in here. So sorry, it's, this is a visual, but that's not all of the information. But good question. Yep.
Thanks, David, again.
Hope that's what you're looking for. Just kind of